Previously, we have discussed discriminant for general module. Now let's focus on the case of extension of number fields. Remember in the introduction we asked, what does a discriminant discriminate? And we say that we're going to use it to discriminate two things, bases and ramified params. So let us start with bases. The setup is going to be, we have an extension L over K of degree n of number fields, and let sigma 1 sigma n be K embeddings from L into an algebraically closed field containing K. Then we claim that we can use discriminant to detect not only bases of L over K, but also integral bases of OL over OK. So how does a discriminant detect bases of L over K? To that end, we need to give another characterization of the discriminant. Observe that given a tuple omega I, the corresponding matrix of the bilinear form corresponding to trace is just gonna be the product of this matrix, sigma I omega j, with its transpose. So then the discriminant of omega I being the determinant of this matrix is just gonna be the square of the determinant of this matrix here. From this, we see then that the discriminant of omega I is non-zero exactly when omega i's are linearly independent, i.e. if and only if they form a basis of L over K. So why is that? Well, this discriminant is non-zero if and only if this determinant is non-zero, i.e. if and only if this matrix here is invertible. Now observe that any relations amongst this omega I leads to a relation amongst the row and vice versa. So the matrix is invertible, i.e. the rows are linearly independent if and only if omega i's are linearly independent. Now there's another way to look at this. If we think column-wise, then if omega i's are linearly independent, but the columns are linearly dependent, then we will get relations among these characters, contradicting the linear independence of characters. From either viewpoints, we see that the determinant of this matrix is non-zero if and only if omega i's are linearly independent. And that is how this discriminant detects a basis of L over K. But we claim that it can do much more. It can actually detect integral basis of OL over OK. Well, first, it can actually prove existence of such an integral basis. The key idea is to use the existence of a dual basis. So observe that the fact that this discriminant is non-zero for a basis means that this bilinear form is non-degenerate. What that means is that for a given omega in L, omega pairs with every element of L to 0 if and only if omega was 0. Another way of saying that is that the natural map from L into the dual space of L, given by sending every omega to the map defined by pairing with omega, so this map is going to be injective, because pairing with omega is 0 if and only if omega itself is 0. However, since dimension of L is equal to the dimension of this space, we see that saying that this map is injective is equivalent to saying that it's a bijection. And thus, given any basis omega 1 omega n of L, there must exist a dual basis eta 1 eta n of L over K, by which we mean the pairing omega I with eta j is going to be equal to delta ij. So let's see how the existence of the dual basis gives us existence of integral basis. We'll prove existence of integral basis in a much more general context. So in our setup, instead of OK, we'll just look at a general integrally closed domain A. That means integrally closed in its field of fraction, which we call K in this case. And we let L be a finite extension of K of degree n. Then we let B be the integral closure of A inside L. Then we claim that B is gonna be contained inside a free A module of rank n. This means in particular that if A is a PID, then B itself must be free of rank n. That is because every submodule of a free module over a PID must be free. Alright, so let's see why B must be contained in a free A module of rank n. Right, so let's pick a basis for L over K. Then from our previous discussion, there must be a dual basis. Thus we can write every element letter B and B as a linear combination of this eta I with coefficient in K. Now we want to prove that these coefficients are gonna lie inside A. Then that would mean that B is contained inside the free A module of rank n with generator eta 1 to eta n. And this is where we use dual basis, because dual basis helps us pick out coefficient. If we apply the dual basis onto B, right, if we apply omega I with the pairing, then we pick out this element alpha I. Now if we pick omega I to be in B to begin with, then omega I times B lies in B. Then omega IB must be integral over A, and so must all of it conjugate. And thus the trace must be integral over A, but the trace lie in K, and A is integrally closed in K, so this trace must lie in A. Alright, so the only thing we need to fill in here is why can we assume that this omega I lies in B? Well, observe that every omega in L satisfies some monic polynomial with coefficient in K. If we let A be the least common multiple of the denominators of these coefficient, and then multiply this with A to the n, then we get a monic polynomial for A omega, but now with coefficient in A instead of in K. So A omega is integral over A, and thus A omega must lie inside B. And thus every element omega in L is going to be of the form something in B divided by something in A. And if eta I over AI is the basis of L over K, right, then since AI lie in K, this eta I must also form a basis of L over K, and thus we can choose a basis of L over K completely lying in B. Thus we have shown that B must lie inside an A module, free A module of rank n. And again, in the case when A is a PID, then B is going to be free of rank n. So for example, when A is Z, then OK is going to be a free Z module of rank n. Note though that OK itself is not always going to be a PID, so OL is not always going to be free over OK of rank n. Now that's about existence, but we can actually construct an integral basis for OK, or actually for any ideal I of OK. And the way we would do it is by choosing a basis of K over Q that lies inside the ideal I, such that it has minimum discriminant. This is discussed more in the video on integral basis. There is also an algorithm for constructing integral basis, which we'll discuss in another video. That is how discriminant helps us detect basis. Next we want to talk about how discriminant helps us detect ramified primes.